good. Hi, everyone. Let's get started. My name is Sirui. I'm a product manager at Databricks, and I'm joined here by Dr. Vijayan Prabhakaran. He hates it when I call him doctor. He's one of our technical leads, one of the geniuses behind Databricks, and we are here to talk to you today about AI-accelerated delta, faster, easier, cheaper. So I'm going to start with this Venn diagram, which maybe you all have seen before, maybe not, but it's a pretty universal concept that we've seen, which is that historically, when it comes to data systems, and really when it comes to your general everyday life, you've had to choose between at most 2 out of the 3 things here, right? Fast, easy, or cheap. So what's an example? So in data systems, for example, you could go and you could just throw money at the problem, right? And that's going to make things fast, and it's pretty easy for you to do, but that's certainly not going to be cheap. And after a while, you might tire of that, and you might roll up your sleeves and do some optimization yourself, and that's going to make things fast and cheap, but it's certainly not going to be easy, right? And so this trade-off is everywhere. It creates quite a bit of a headache, right? Think about all the knobs you have to twist and turn to even just start making these trade-offs. And so in the data storage space, which is the space where myself and Vijayan swim in, we find that this trade-off is everywhere, right? So think about tuning file sizes. No one wants to tune file sizes, but this trade-off is there, right? Do you work to tune those file sizes? Is it worth it? Are they too big? Are they too small? Is that going to make things that much faster or cheaper or easier? I don't know, right? Balancing read versus write performance is another example. We see this a lot where you have those choose two trade-offs, but on top of that, there's another dimension of trade-offs, which is, do I optimize for read performance or write performance? Because those two are usually trade-offs against each other as well. Partitioning and clustering. Right? Do I partition my columns? Do I cluster my columns? When you actually go and do this, does it actually work, or does it make things worse? What a headache. And after all that, you might do all those first 3 things here, but things change on you over time, right? Your data changes, your usage patterns change, and you have to change maybe the way you do maintenance and clean up on your tables on top of all that. So all this is a headache. Actually, show of hands here. Who here has dealt with at least one of these problems? OK, good. That's most of you. Most of you. And if you haven't, then I think my question to you is maybe you're going the easy route and you're leaving some price savings on the table or some query performance on the table. Right? So, all right, enough talking about problems. Let's talk about solutions. So the core thesis of our talk today is that with AI-accelerated delta, we have an opportunity here to let you choose all 3. It's not really a choice. You just get all 3 of these things, right? So that's faster query performance, and at the same time, that's lower overall TCO, all without needing a team of PhDs to actually go and do this for you. It's a pretty bold claim, and I'm going to try to back it up. Vijayan and I are going to try and back this up over the next 37 minutes or so. So how are we going to do it? So first, we're going to start with Delta Lake, which I'm sure you've heard a lot about this conference. Delta Lake is going to be an open storage format, right? It's an open source storage format. It's a universal storage format. So as you may have heard now with the new uniform announcement, if you store in Delta Lake, you can read it as Iceberg or Hudi or Delta. And it's a performance storage format. Right, super fast. So we'll talk a little bit more about that. But even the fastest race car needs a good driver, right? And so in the Databricks Lakehouse, we drive Delta with what we call Lakehouse AI, with our own AI product. And what that does is it gives a layer of AI intelligence to help drive Delta, right, to help make things faster, cheaper, and easier. And we've trained that AI on years of operational expertise running tens of thousands of anonymized production workloads. Right, and you put those 2 together, and that's what we call AI-accelerated delta for the Databricks Lakehouse. And it's an AI model or a set of AI models that are purpose-built to tackle the challenges that you just saw before for you so that we can make things faster, cheaper, and easier without you having to roll up your sleeves and do things yourself. All right, let me take a little bit of a detour to motivate where our North Star is with AI-accelerated delta. So AI in writing. Let's make an analogy. So in writing, right, it's also a space with a similar trade-off. So if you think about what it takes to write well today, like let's say you're in a business setting or even a personal setting, what does it take to write well? Well, you're also in this trade-off space because if you want to write something well, you could do it yourself. And that's going to be hard, but that's also kind of cheap because you're not at least paying anything. Or you could go and hire a team of copywriters to do that writing for you, and that's going to be, well, it's easy for you, but it's also expensive because that kind of talent's expensive. Right? But what we've seen over the years is with advances in AI, we've started to climb this curve and to really change that trade-off dynamic. Right? And so, for example, in the 90s and the 80s, you saw like spell check and grammar check, right? Those squigglies in Microsoft Office. That helps make things a little bit easier. Right? Now you no longer have to worry about like spelling and grammar check. More recently, we had things like services that helped you with basic diction and voice. So avoid the passive voice, that kind of thing. But as I'm sure you all know where I'm headed with this, and I'm sure you've all played with the latest large language models, you have finally support for full-on authoring, right, with AI. And so at the top of this curve, what does life look like for authoring? Right, you're still in control. You still control what you want to write and what the content is, basically, and what you want to use the writing for. But AI has fundamentally changed the trade-offs here, right? Because now you can write faster and easier and cheaper at the same time. Right? So with AI accelerated delta, we want to climb the same curve right before your data. And when you get to the top of that curve, my promise to you is that you'll still be in control of your data, like you still control what to ingest and when and what to use that data for. But the AI accelerated delta is going to make things faster, cheaper, and easier for you. It's going to change that trade-off equation the same way that LLMs and all the other tools did it in writing. And so specifically what that means is lightning fast, super simple ETL, cutting-edge query price performance, data that gets cheaper and faster with use. So the more you use it, the better it's going to get, all of which is still fully open. And that's the critical part. It's still in an open source format. It's still in a lakehouse that you own. Right? So you own the data. You can query it however you want, but you still get those first three benefits. All right, so I'm going to back all those promises up because that's a hefty claim to make. And what we're going to do is for the rest of the talk, we're going to climb this curve, and we're going to talk about the challenges, and we're going to talk about what we're doing with AI accelerated delta to actually tackle those challenges. So the first thing I'm going to start with is file sizes. All right, so what's the problem with file sizes? So in any open lakehouse table format, as I'm sure many of you know, like Delta, Iceberg, or Hootie, these formats are actually made of multiple data files. And every time you write to the table, you're writing more files. So this comes with a set of challenges. Because first, and we see this very often, your file sizes might be too small. So imagine a single table. Maybe it's not even that big, but you write to it a lot, so it's made up of millions of data files. Right? And just imagine doing a read against that table. You've got to comb through a million files. It's going to be really expensive, and things are going to slow to a crawl. But separately, the other extreme is also bad. So imagine now a table, maybe it's huge, maybe it's not, but it's made up of just a few super large files. That's also bad for performance because it inhibits your ability to do things like efficient data skipping, right? You have to read this entire file just to get to like one row. Okay? So the challenges here are twofold. The first one is this is sort of a Goldilocks problem, right? Where's the right middle ground between too small and too large? Right? And secondly, even if you know what that perfect middle ground is, how do you make sure that your file sizes are actually at that Goldilocks zone in practice? Okay. So what do we do here? We did something we call AI-optimized file sizes. And so what we did was AI is really good at finding the Goldilocks zones, right? Finding the balance between too big or too small or too hot or too cold or what have you. And so first thing we did was we built an AI model of the ideal file sizes for a given workload. So we fed in this model all of our anonymized production data, right? And it includes things like how many tables are there, what are the sizes of the tables, what are the file size distributions of the tables, the query performance, existing query performance against the tables, right? And this model outputs what it thinks is the ideal file size for that workload. We made sure to rigorously do a lot of benchmarking internally to make sure we had really high confidence in this data. Right. And for those of you who are wondering, like, what is the ideal file size? Well, it depends on a lot of factors. But for example, when we looked at a typical 1 terabyte table with typical read-write patterns, the ideal file size was between 60 to 100 megabytes. So that's the general range we're looking for. And when we looked in the fleet, I don't know if you guys know your file size distributions, but when we looked in the fleet, we saw that in practice, file sizes were way smaller than that, like orders of magnitude smaller than that. So we knew we had a big opportunity here. Next, we wanted to start nudging file sizes closer towards that ideal. And so what we did was we improved how our clusters and SQL warehouses performed writes to start nudging files towards being larger. So this included doing things like coalescing multiple write tasks together. So there's fewer tasks writing fewer files, which are larger. And it also included doing things like making sure with some background spare compute that we had, that we could opportunistically compact some files together. So some mumbo jumbo there, but we'll talk about what the results are. The status is that this is actually already GA'd and rolled out by default in UC managed tables with the latest runtimes. So if you're using, say, DB-SQL to do your writes and you're using UC managed tables, then you're probably already using this without you even knowing. And it's coming soon to UC external tables as well. So let's see what the results are. So the first thing I'll say is when we rolled this out, we had a lot of telemetry around, are we actually moving file sizes towards that optimal ideal? And what we found is that our two methods, right, reducing the amount of tasks, that made a 6x improvement in the ingestion time. And then our background compactions, where we're using your spare cycles to compact files, that did a 30x improvement in file sizes. And this is good because we knew with confidence that getting file sizes larger would mean better performance. So in our benchmarkings, what we saw is that if your tables go through this type of dramatic file right sizing, that you would expect over a 2x improvement in query performance. All right, so faster queries, and also cheaper because you're spending hopefully half as much time on your compute, which means half as big of a bill. But it's also simpler as well, right? Because there are a number of settings, thanks to this capability, there are a number of settings that you used to have to set that you no longer have to set. So one really good example of this is the setting we used to have called target file size. So this is a setting where you as a customer could tell Delta, well, I want my file sizes to be 10 megabytes or 20 megabytes or what have you, right? And we've heard from some more advanced customers, they would roll up their sleeves and they would say, hey, I'm going to just do a bunch of trial and error. I'm going to try a 10 megabyte file size and a 20 and a 40. I'm going to benchmark that, and I'm going to get to my ideal. What a headache. But then even worse, if their workloads changed over time, or if they just have different workloads, they'd have to do that over and over again, right? So with our AI model, which determines the target file size for you, we're really pleased to say, hey, you don't have to set that anymore. If you don't set it, we're just going to figure it out for you. Right? And that's true for the other knobs as well. I don't have time to go into all of them. But overall, the message here, a takeaway is that with AI-optimized file sizes, we're already making your workloads faster, cheaper, and easier. All right, let's keep climbing the curve. So next I'll talk about updates, the challenge of making efficient updates. So what is this challenge? All right, so with this, I'm going to introduce a toy example that we'll come back to over and over again. So in this example, you have a single table. It's made up of 3 data files, 1, 2, and 3. And all you want to do is remove the rows that are shown in red right there. So how do you do that? So in every lakehouse format today, the default is a method called copy on write. And so what that method does, right, is really simple. You just rewrite all of your data into files 4, 5, and 6, but you don't write the deleted rows. Now, gosh, hopefully the problem is already pretty obvious, because now just doing that delete, you make a lot of expensive writes. Right? You're rewriting files 4, 5, and 6, most of the files. Right? So you think, maybe we can do better than that. Right? And what if we don't rewrite the files? So then we come up with a method called merge on read. So this method says, we're not going to rewrite files 1, 2, and 3. All we do is we add a single log file, and that log file says that such and such rows are deleted. And so it's now up to the reader to merge all that information together, right? The reader reads files 1, 2, and 3. It reads the log file. It says, OK, now I know what rows exist and what rows don't exist. All right, so are we out of the woods? No, because now you need to worry about when to use one or the other. Right? So in copy on write, the first method, your writes are really expensive, but your reads are cheap. Your reader just needs to read these like very normal files 4, 5, and 6. In the merge on read case, right, your updates are very cheap. You're just writing a single log file. You're not doing the rewrites. But now your reads are expensive, because your reader needs to merge a bunch of files together. Right? So which one do you choose for which use cases? You have to kind of decide, right? Secondly, maybe you say, OK, actually, merge on read is the thing for me. You have a second problem here, which is that with merge on read, as you make more and more updates to this file, you're writing more and more log files. Right? And the problem is that makes life harder and harder for the reader. So imagine a reader that's reading a table with 3 data files, but like 300 log files. And it's got to do all that merge. Your read performance is going to slow to a crawl. And we see this in practice with a lot of tables that do use merge on read across the other formats. And so what you do is you can periodically do this thing called purging a log file, which is basically just looking at all those files, looking at all the log files, and just doing the rewrite. So now you have files 4, 5, and 6, and it incorporates all the log files together. Right? But now that's another problem for you, because how often do you do that purging? Right? If you do that purging too often, you're back to the very first problem, where you're just rewriting stuff over and over again. But if you do it not often enough, right, then your reads slow to a crawl. So what I've presented here, yet again, is another set of Goldilocks problems, right? Where is that perfect middle ground between when to use copy on write versus merge on read? And where's the perfect middle ground between whether or not to purge log files or keep them around, right? So what do we do? All right, Probably not a shock, we're going to use AI again. And the capability we released is called Predictive IO for updates. And so what we're going to do is, what we've done is we've used AI to intelligently find that Goldilocks zone for you. All right, so what it's going to do is it's going to decide when to use merge on read versus copy on write. If it's going to use merge on read, if it's going to use those log files, it's going to make sure that there's super optimized bitmaps that can be prefetched with Photon and things like that. And then also it's going to decide for you how often to purge those log files based on your query patterns and things like that. So should I leave those log files around, or should I go and purge them? How often do I do that? Status of this, public preview. So you can actually use this today. Let's take a look at the results. So the first thing we noticed, we're going to compare here in these benchmarks, Predictive IO for updates. That's the new thing we're talking about, against copy on write. The first thing we noticed was an order of magnitude improvement in update and write performance. So this is because you're not rewriting the whole file again. You can just use those hyper-optimized log files where necessary to make those writes and updates really fast. But if you recall, the Achilles heel for merge on read for those log files was the read performance. And that's why we were really excited to see that for this technique, the read performance was virtually unchanged from before. And that's because our log files are hyper-optimized. And it's also because we're intelligently doing away with those log files when we can to make read really cheap. But also, not only is it faster and cheaper by an order of magnitude sometimes, it's also easier, right? So you no longer need to choose between copy on write versus merge on read. You don't need to listen to the same lecture that I just gave. You don't need to choose when to purge those log files. You just turn this capability on and you get the best of all worlds. All right, we're going to keep climbing the curve, and now we're getting to the really exciting stuff. So I'm going to hand it over to Vijayan. He's going to take us home.
As we climb the curve of AI-accelerated delta, our next stop is clustering. Clustering is a very well-studied topic in the field of databases because it's a hard problem. Take partitioning, for example. Partitioning is good for performance if done correctly. However, partitioning comes with a lot of challenges that are harder to solve even for the most expert user. For example, what columns do you use to partition your table by? One of the common patterns for our customers is to use a date column to partition their table so that they can group related data by, say, a week, month, or by year. However, if we accidentally partition the table by a timestamp column, which actually happens in practice, then this can lead to a lot of small files leading to extremely poor query performance. What if the column we choose to partition the table has very high cardinality? And what if the column we choose to partition has low cardinality initially, but started getting higher cardinality over time? Even if you know how to solve all of this problem, there are several other challenges that come with Hive-style partitioning. And I'll try to illustrate that with the help of an example. Here, I'm showing a table that is partitioned in a Hive-style fashion across two columns, a customer ID column and a date column. Each cell in this diagram represents a single partition, and the black boxes within each of the cell represents the number and size of the files within that partition. And these files belong to a specific customer ID and date pair. Ideally, what we want is that the files to have the right size and also well clustered. However, this is extremely hard to get right in practice. As you can see in this example, the number and size of the files across these partitions can vary dramatically. In fact, there can even be partitions without any data. Let's say we have this table, and suppose we want to scan 1 hour worth of data from the whale customer. This whale customer has a lot of data, and the data is queued and stored on very large files on a single partition. So even though our query wants to read only 1 hour worth of data, it still has to read all those really large files, leading to poor query performance. For this customer, we may want to rethink our partitioning strategy to partition the table by, say, on an hourly basis. Suppose we have a different workload that wants to scan 1 year worth of data for the Tiny2 customer. Tiny2 customer, on the other hand, has very little data that are over-partitioned and stored on really small files, and a lot of them. In this case, now the query has to issue a lot of cloud storage IOs, which again affects the query performance. For the tiny 2 customer, again, we have to rethink our partitioning strategy to maybe partition by a monthly basis or even by an yearly basis. So even when you have a well thought out partition strategy, your table can both be over partitioned and under partitioned at the same time. Let's say that we figured out a partition key that works across all the customers, and we want to change the partition key. And if you want to change the partition key, now we have to rewrite the entire table again. Let's say that we are even okay with rewriting the table once, but what if the workload continuously changes? Like instead of ingesting the data once every day, we start ingesting the data every hour. What if the data we ingest contains information across a lot of customers that gets sparsely spread across a lot of small files? In order to handle this dynamically changing workload conditions, now we have to set up maintenance operations that will combine these small files into right-sized files. We want to solve this problem for you, and we are solving this by introducing liquid clustering. Liquid clustering will make your delta go faster, cheaper, and easier. With liquid clustering, the ingestion is much, much faster compared to hive-style partitioning while giving similar read performance. And liquid clustering is also self-tuning in nature. That is, it adapts to the changing workload conditions to avoid either over-partitioning or under-partitioning your data. It also works in an incremental fashion. That is, when new data gets ingested, it only partially clusters the newly ingested data without having to rewrite the data over and over again. And more importantly, it is skew resistant. Remember the case where we had the customer with a large amount of data stored in very few files? It handles such skew scenarios very well by consistently producing good-sized files with minimal write amplification. And finally, it is super flexible. If you want to change the partitioning key, you can do so anytime without having to rewrite the data. I'll try to illustrate how liquid clustering works by using the same example. Let's say for customer B, we have a lot of small files spread across many dates. Liquid clustering automatically identifies this scenario and carefully reclusters the data into a set of few right-sized files. Let's say on a single day, we started ingesting data that is fragmented across many customers. Again, liquid clustering identifies this and regroups the data into a set of fewer files that are needed. And this not only works across individual dimension, but even on a multi-dimensional space, liquid clustering can identify a set of really small files, and it can rearrange them into as few files as necessary. Liquid clustering can not only regroup small files into large files, but it can also subdivide larger files into smaller files. Let's take the same example where this particular customer had a lot of data stored on one single partition. Liquid clustering can now subdivide this partition into a set of smaller partitions, leading to better file sizes and much better data skipping. And the way it works is that when the data is ingested, this data is written into as few files as necessary and as quickly as possible. As the data accumulates over time, they get clustered across a few partitions, groups of clusters of data as necessary. And in the background, the data gets compacted into a set of few right-sized files. The important thing to note here is that all of this are done automatically. That is, liquid clustering is the one that is making decisions about the data cardinality, how to group the data, how to rearrange the data, and not the end users. Let's look at some performance numbers. We compared liquid clustering against two popular partitioning strategies. One, hive-style partitioning. The other, z-order-based clustering. On the figure here, we are showing the ingestion performance. And the green bar here represents the time taken to ingest the data. So the lower, the better. When we ran this benchmark against Hive-style partitioning, it took so long, we actually had to kill the benchmark. And you can see that liquid clustering gives the best ingestion performance among all the techniques. The yellow bar here shows the write amplification overhead from liquid clustering. Write amplification happens when you rewrite the same data over and over again in the process of clustering. Even though Z-order clustering gives better ingestion performance compared to Hive-style partitioning, it still results in higher write amplification overhead. Liquid clustering, on the other hand, gives the best of both the world, where it gives it gives much better ingestion performance with minimal write amplification overhead. All right, how does liquid clustering perform on a scan? So in this graph, we are showing the scan performance. The y-axis represents the time taken to read the data, and the blue line here represents the time taken when we ran the Z-order-based benchmark. As you can see, when all the data are clustered, Z-order-based clustering actually gives pretty good performance. But as data gets ingested, its clustering quality starts degrading over time, leading to poorer performance. So the read performance starts degrading, like the read time starts increasing. If the data gets reclustered again, Z-order-based clustering starts working well again. This leads to the zigzag pattern in the Z-order-based clustering, leading to valleys and cliffs that can result in highly inconsistent query performance. Liquid clustering, on the other hand, only partially reclusters. Okay. Liquid clustering, on the other hand, only partially reclusters the newly ingested data without having to overwrite the data over and over again. So with liquid clustering, you get faster ingestion, similar read performance. So with that, now your queries are cheaper to run. And it is also extremely easy to use because as an end user, you don't have to worry about data cardinality, changing workload conditions, or changing data characteristics. All right, we have climbed the curve, and now we have reached the summit. Now we want to tackle the problem of continuous optimizations. We all know that we have to run maintenance operations regularly in order to improve the table performance. And there are a number of maintenance operations. For example, customers often run optimize to regroup smaller files into larger files. They run clustering to group related data together. You can run vacuum to clean up the deleted data, or analyze to collect more table statistics in order to improve the query performance. However, one of the biggest challenges customers face today is they do not know on what table to run these operations, which operation to run, how often to run, when to run. So because of this, customers end up choosing one of the two paths. They either don't run any operation at all, which can lead to significantly poor query performance, or they run most of these operations on all their tables, which can be super expensive. Even if you know how to run these operations, you still have to put effort to write the code to run these operations, set up a job to run them, monitor this job, provide the right resources for the job to run these operations. We want to solve this problem with the help of predictive optimization. Predictive optimization is a new AI-driven technique that automatically figures out what table to optimize, what operations to run on those tables, when to run them, and how often to run them. Once these decisions are made, we take these decisions and run them on our hyper-optimized serverless infrastructure in order to run them as efficiently as possible. Predictive optimization has a number of applications. Let's take a look at clustering. As I mentioned before, liquid clustering works with the changing workload conditions. It works in an incremental fashion. It adapts itself to the changing workload conditions. When combined with predictive optimization, now you get predictive liquid clustering, where the system automatically figures out which one of your tables require clustering and what columns to cluster the table by. And in the background, it automatically triggers liquid clustering to group the related data together. At a very high level, the same intelligent decision-making framework is also used to run other maintenance operations, such as optimize to group the small files, vacuuming, collecting additional table statistics for storage tiering, and so on. Let's take a deeper look at how predictive optimization works. Predictive optimization uses an AI model that has been trained on millions of data points from our operational history. We collect a number of parameters. For example, we look at table usage characteristics, whether a table is heavily used or it's lightly used. We also look at the performance of the table. For example, how long does it take to run a query on the table? We also look at very specific tables characteristics, such as number of files the table has, like the size of the files, how many partitions does the table have. We don't look at an individual data point. Instead, we collect a history of such information for the table and feed this information into the AI model, which then uses this information to calculate two things. First, it calculates the cost to run a maintenance operation. And then it also uses the information to estimate a benefit that would come after running this maintenance operation. With this cost and benefit, the system now calculates a return on investment for each table and each operation. Once such a return on investment is calculated for every table and every operation, we then pick those tables with the highest ROI and then give it to our intelligent scheduler. This scheduler now packs these operations as efficiently as possible and runs them on our hyper-optimized serverless infrastructure. When these operations are run, we take the output of these operations and store them on the system table. I'll take all the questions towards the end of the talk. All right, so let's take an example, and I'll show you how this works. Okay, let's assume that we have 4 tables, table 1 to 4. And table 1, let's assume that it's not heavily used. Let's say it's kind of like a temp table. On the other hand, tables 2 to 4 are more heavily used. And the system wants to calculate the ROI for the optimize operation. So the system now calculates what is the cost of running optimize on this table. For some table, the cost of running the optimize might be pretty low because there may not be enough data to compact, or the table itself might already have right-sized files. It also calculates the query speed up that the system would get after optimizing the table. Again, for some table, the query speed up might be pretty high because it has a lot of data stored across many small files. Once this is calculated, the system estimates a return on investment for each of the table and then sorts all the table and ignores the tables with the low return on investment for the optimize operation. A similar estimate is made for all the other maintenance operation as well. For example, let's take the case of vacuum. For vacuum, the system calculates what's the cost of running the vacuum, like the number of deletes that it has to issue, and what's the benefit that you would get by running vacuum, like how much data, gigabytes or terabytes of data that can be cleaned up. And a similar ROI will be calculated, and tables with low ROI will again be ignored. And then the system picks a set of tables with high ROI. Let's say in this case, we want to run vacuum on tables 1 and 3 and optimize on tables 2 and 4. And then the system packs these operations and runs them on our serverless infrastructure. And when these operations are done, we collect the information and store it in the system table. Notice that when we run this on the serverless infrastructure, again, the system automatically picks up what compute node to use, how many nodes to provision, whether to use auto-scaling or not. All of these decisions are made on behalf of you. You don't have to worry about any of this. Hope I have given a good overview of liquid clustering and predictive optimization. Now I'll hand it over to Sirui, who will talk about the performance benefits from the system.
Yeah, give it up. All right, now the cool stuff is out of the way. I get to end this thing. So All right, so predictive optimization has been in private preview for just a few weeks now, but I wanted to present a case study based on what we've learned working with our customers. And so the first thing I'll start with is a lot of customers are in this zone right here, which is that they don't do any optimization. After all, this is the easiest thing to do is you just don't optimize your tables over time. So what's wrong with this? Well, first of all, you're not getting as great query performance as you could be because your tables aren't as optimized, and also your costs may not be as good as they should be because any compute that talks to these tables, it's crunching a lot of numbers that it doesn't have to. On the other end of the spectrum is a customer who I call them the kitchen sink customer. They just throw everything at everything. So they might choose most of their tables, they run a daily job, and they basically run every single optimization there is, Z-order, optimize, analyze, all that good stuff. The problem here is, well, first of all, you're going to get great query performance, but also your costs may not be as great as they could be, because the problem here is you might be optimizing tables that no one's actually querying. And even for the tables that people are querying, you might be hitting this point of diminishing returns, where you're not, each bit of compute that you spend optimizing may not be getting as much return on investment as you like. And so what we saw with predictive optimization is that we were able to find, yet again, this Goldilocks zone, where query performance is just as good, especially for the tables that you really care about, but that we're actually saving costs relative to both approaches because we're able to find just the right return on investment operations to run. So don't just take my word for it. So you saw, maybe you recall in Reynolds' keynote that he had a quote, similar story from Anchor. I have another customer, Dexco. I won't read that quote, but basically they turned this thing on. It's just a flip of a switch. You turn it on, and what they saw was, first of all, that predictive optimization was able to quickly identify what tables really mattered to them. It was able to double the query performance on those tables, while also providing overall cost savings because of less compute needed, because it was able to delete some unneeded data. And the team didn't have to lift a finger beyond just flipping a little toggle in the UI. So if that ain't faster, cheaper, and easier, I don't know what is. This is in private preview, by the way. It's going to go public preview in a month or two. But talk to your account team if you want to try this out right away. We're super excited about it. All right, we're at the end of the journey. We're at the summit. Let's put it all together. So I'm going to revisit the promises I made at the top of the talk, and let's see what we've learned. So I promised lightning fast, super simple ETL, and we saw how, as you're doing ingestion, right, you no longer need to worry about file sizes. Partitioning strategy becomes a lot easier thanks to liquid clustering. I promised cutting-edge query price performance, and we saw, for example, how with Predictive IO for updates, you get really fast, order of magnitude better update performance while keeping read performance just as fast as it ever was. I promised you that data would get even faster and cheaper as you used it, and we saw how with liquid clustering and predictive optimization, we learn, right, what columns and what rows are important for you, and we optimize your data around that. We cluster your data based on what columns are important. And finally, and I can't stress this enough, it's fully open, right? So we do all this optimization when we're writing out the data, but at the end of the day, it lands in Delta, which is an open format, in an open data lakehouse where you control the data. It's still in your storage account. And so you can read this anywhere and any way you like. Okay, so at the end of the day, it's AI accelerated Delta, faster, easier, and cheaper. So I'll leave you with this. None of this is science fiction. It's all available today. I can talk about benchmarks, and I can make promises till I turn blue, until the cows go home. But I invite you actually all to try this out today. The steps are over there, and see for yourself how AI accelerated Delta can help you. So with that, thank you very much.